Hello, everyone, and today we're going to be finishing up our description of physical mixtures by talking about that ever messy topic, three-component mixtures, more commonly known in PChem as a ternary mixture. So, as you may imagine, once we go to three components, systems are going to start becoming a little bit messy, just as they did when we went from a single component to two components. And we can kind of track out one of the reasons why these systems become so messy by looking at our phase equilibrium, because that's mostly what we've been tracking when we've been looking at phase diagrams of a two-component system. Now, when we were looking at a single phase, so a single compound, and looking at its phase equilibrium, we've got one component and two phases, and this means that we have 1 degree of freedom. And we saw this with things such as looking at water. When I had just the one component, as long as I knew the temperature the system was at, I also knew the vapor pressure at which the system would come to equilibrium. However, as soon as I added a second component, things got a little bit messy. Because at this point, now I've got two different components, but I still am only going to have two phases. And this means we've got 2 degrees of freedom. And as we saw previously, our choice is to typically keep the pressure constant and then look at how the boiling point or the temperature changes as a function of the composition of the system. But as we also demonstrated, you can examine how the vapor pressure is also going to change as a function of the composition under constant temperature. But it's very hard to kind of illustrate both. Now, this problem becomes much worse once we reach a ternary mixture. Because once I've got 3 components, well, at this point now I've got 3 separate degrees of freedom. So this is going to greatly change how I describe my system. So for example, if I go ahead and look at a ternary system of A, B, and C, well, now we have to essentially find a way to fairly easily describe 3 different variables. And so our choice is going to be typically to fix pressure and temperature, and then essentially look at what point our remaining 2 variables come into equilibrium. So essentially, where phase equilibrium happens with regard to the composition of 2 of our 3 components. So in this case, we're typically going to choose the mole fraction of A and B, because once I've defined the mole fraction of these 2 components, I've perfectly defined the mole fraction of C, as the 3 have to end up equaling 1. So essentially what I have is I'm going to be looking at the variance of 2 variables, and then looking at what point I'm going to run into a phase equilibrium with respect to these 2 variables, giving me essentially, if I know the system is at equilibrium and I know one of these variables, I should be able to determine the other. However, in order to describe how the composition of these 2 variables relates to phase equilibrium, first I have to come up with a convenient graphical form to, well, describe the composition of a system. And this can be a bit tricky because we're going to have to use more or less a much different notation, because there is a certain degree of correlation in between our composition of A and B. So what we're going to use is what's called a ternary phase diagram. And so what this does is it lets us relate the composition of A, B, and C to each other. Because I know A, B, and C, when added together, should all equal 1, which makes trying to use a classic right angle diagram a little bit messy. And so instead, what we're going to use is a triangular diagram. And each of these vertices is going to represent a pure phase. So for example, if we go to the top of our diagram, this is going to represent pure A. And then as I move down away from the top of this diagram, I'm going to have essentially less and less A present. And each of these lesser degrees can be shown by a line parallel to our vertice at the top, where the first line here represents 90% A, then 80, then 70, then 60, then 50, 40, and so on until we get to this very bottom line where I have no A at all, and the system is just B and C. Well, we can go ahead and repeat the same process with the other two vertices, where the one on the right here represents B, and the one on the left represents C. So here on the right, we have pure B, then I've got 90, 80, 70, 60, 50, 40, 30, 20, until we get to this very last line where there's no B present at all. And you can illustrate these compositions by taking each of these parallel lines and then going to the right. So essentially, if I'm moving away from B, I can then go to the right, and I'm going to find a number written down that shows the mole fraction of the species of interest. And this is where axis labels can be very important. For example, if I'm looking at looking for a system that is 40% B, so has a mole fraction of 0.4, I can essentially go to this line and then follow it up and to the right. Conversely, if I'm looking for C, I'm going to find the axis of pure C, and then find the line of interest, and then follow it up and to the right. In this case, it would be a fraction of about 0.6C. And again, this will go all the way down till we reach the base of the diagram that is opposite of the C-axis, at which point I've got no C. So some of the easy points to try and observe and keep in mind are, again, our pure points, where here I have pure A, because I'm at here, go to the right, I find a 1, go to the left, I find a 0, go to the right, I find a 0, and go to the right, and again, I find a 0. So mole fraction of 1 of A, 0 of B, and 0 of C. And you can, again, do this for any point. And this is actually fairly nice because as soon as I put a point on the diagram, I perfectly describe the mixture of the species. So for example, if I go ahead and I look at this point, I'll start by looking at A, which is again at the top. So I'm going to find the lines that are parallel to the top and follow them to the right, at which point I've got 50% A. Then I'm going to go ahead and look for the lines that are parallel to B, follow them to the right, 10% B, and then the lines that are opposite C, so that's going to be these ones, follow them to the right, and 40% C. And again, you can always double check that these add up to 1. If they don't, it's usually an indicator that you misread one of these diagrams and you can try again. And don't worry, it does take a while to get used to them. However, this just essentially describes the mixture of describes a mixture that has come to essentially complete equilibrium, and I see no phase separation. It's miscible in all mole fractions of all three components. However, that's not always the case. We'll often find systems where the three components may end up separating out into 2 or more phases. So one of the easiest descriptions is, for example, a liquid mixture of A, B, and C. And what we're going to do is essentially divide our graph into 2 major regions. One, where everything is completely miscible. You can often find the regions where everything forms a single phase because they'll tend to include our 3 vertices, which again makes sense because a system that is pure A, B, or C should be, well, completely miscible because we generally expect our pure phases to not split in part. And this means that the remaining region is going to be a 2 or 3 component phase. And most of the time, these are going to be fairly well diagrammed of what they describe. In this case, it's saying that this system will split into 2 different phases. Now, this leads us to a slight problem of how do I figure out what the composition of the 2 phases that I split apart into are? And this can be a bit messy. So in order to understand this, we usually need to first start by identifying a key point. And this is called the Platt point. And this is essentially the critical point for phase separation. It's going to, again, be perfectly defined. This is going to be the point at which phase separation of my immiscible phases just begins. So this means that when I take my pure phase and it just begins to separate out into two separate phases, but those two separate phases have the same composition or almost the identical composition of the phase I started with. Unlike over here, where I'm going to generate a phase that's a very different composition. And this plat point is very important and actually fairly useful. However, in order to more quantitatively describe how my system goes ahead and splits apart into separate phases, I'm going to need to make use of tie lines, just like I did for a binary system. However, the big thing with tie lines in a ternary system, rather like the plat point, is these tend to need to be experimentally determined. You can't just kind of eye guess, this is where I start to see um, this is where I start to see a curve. This is where the plat point should occur. It may or may not be present there. It may be present to the right or the left. It's often going to be placed on the diagram. When it's not, it can be difficult to essentially interpret how the system splits apart. However, once you have the plat point and the tie lines, what you can do is essentially examine how the system splits apart. For example, if I go ahead and have a mixture at this point, I know that it should essentially split apart into a fraction that is more of a mixture of B with a little bit of A and C present. And again, we can figure out this composition. And note that it's mostly B rich by following it down to the right, and we find that it's a little bit more than 50% B. But by this point, it's almost entirely B. And it's also going to split into a mixture that's very C-rich with a small fraction of A and B. And we can generate this again by seeing, going to the right, it's about 80% B, about 10%, a little less than 10% B, and a little bit more than 10% A. And again, using these diagrams, you can figure out what my original mixture was and how it's going to split apart. And then, unfortunately, you need to be able to do a little bit more tricky geometry in order to define the length of your tie lines. But however, once you do know the length of your tie lines, you can use the same tricks of the lever rule that we did for binary systems, because the lever rule is pretty much for everything. However, you can also apply these general concepts to real mixtures such as ethanol, water, and chloroform. So if I've got a system like ethanol, water, and chloroform, I can, for example, take a real mixture, use it to inform real processes, such as taking a mixture of water and chloroform, and then seeing what happens when I add a little bit of ethanol. And so again, you'll note that this diagram has already denoted the plat point and several tie lines that I can go ahead and make use of. And so what we're going to do is I can first identify, if I start here at point A1, I can identify that the system is a little bit less than 60% water and a little bit more than 40% tetrachloromethane, also another name for chloroform. And so this is actually fairly useful. However, you'll note that this area lies within the two-phase mixture, which means it's going to split apart. And you may say, I don't have a tie line here. But it turns out you're always given one tie line for free. It's the base of the diagram. So at this point, my mixture of water and toluene is going to separate out into one fraction that is a little bit less than 80% water, and one fraction over here, denoted by T, that is a little bit less than 10% water, probably closer to about 5%. And again, that means it's going to be 95% uh, chloroform, and that this one, again, if we follow it back, should be roughly about this one, as you've noticed, is clearly defined as about 13% chloroform. So again, we can make use of these. And again, remember, always try and follow it to the right. When you follow it to the left, you do what I accidentally did there and try and go onto the ethanol diagram. However, what we can do is see what happens when I add a little bit of ethanol. And for this, we can make use of a fun trick. That if I go ahead and draw a line in between the mixture that I have and the component that I'm adding or removing, in this case ethanol, what we have is a line that denotes a constant ratio of the other two species, in this case, water and chloroform. So what I can do is essentially see at which point the system will essentially become completely miscible. So how much ethanol do I have to add until, say, my water will completely dissolve in my chloroform? And you can imagine that something like this can have a lot of importance with things such as preparing samples or trying to drive mixtures of NMR solvents into essentially a complete mixture that isn't going to separate out and ruin your spectra. So when we do this, we can essentially, again, track the line back, and we'll find the system now becomes completely miscible at this point A3. And we can identify this point by, again, following our three lines. So if I'm looking at the ethanol composition, I'm going to follow the line to the right and find that I'm a little bit more than 30% ethanol. Follow my line to the right and down again to find that I'm a little bit less than 30% chloroform, and again follow the line up and right to find that I'm a little bit less than 40% water. And adding these together, we should note that we're about 100% something. However, again, make note that using these ternary diagrams can be a little bit tricky, but a lot of the basic rules, such as the use of tie lines and the lever rule, are going to be constant no matter the diagram we're using, whether it's binary or ternary. However, it's worth noting that a lot of times we're dealing with ternary mixtures that are even more complicated than this three-component solvents, because we may have solids, and these solids may also form metallic alloys. So for example, we can look at the phase diagram for iron, nickel, and chromium. And this particular phase diagram is very important as it describes the formation of stainless steel. So one of the ideas of stainless steel is you're going to take iron, and instead of just putting in carbon like you normally would, what you can do is add in nickel to make it more resistant to acid, and add in chromium to make it more resistant to oxidation. And by pairing these two systems, you can actually make an iron alloy that's much more resistant to corrosion, thus the stainless and stainless steel. However, one of the things to watch out for is that many of these ternary solid diagrams can include a lot of issues. So for example, that it can include single phases with variable composition. In this case, iron nickel. So our gamma iron nickel can include anything ranging from pure nickel to with a little bit of iron present to pure iron with a little bit of nickel present. However, it also can essentially accommodate a certain amount of chromium until you essentially get to above this rather messy phase line. And above this point, you can actually also run into some other problems. So for example, over here on the upper left, you're going to note that this is going to be a system that's much more rich in iron, that however, once we start adding in certain amounts of nickel, but keep the chromium fairly low, we're going to run into several different allotropes of iron that are largely going to be driven by the presence of nickel. That's the reason why this contaminated iron region looks so very messy. And then finally, we're going to find regions where we have a great deal of phase separation. So for example, if I include fairly high chromium levels, what we may find is that my gamma iron nickel is going to start throwing out some solid chromium, which is going to phase separate out from the original uh, nickel complex that I'm trying to form. And then once I get into this region, well, let me just tell you, it gets rather messy as you'll be throwing out several of these allotropes along with chromium and the iron nickel. However, there is some important points that we can observe, such as this point A, which is actually the very definition of stainless steel. So stainless steel here is a little bit less than 80%, about 75% iron, and about uh, 5% nickel, and a little bit less than 20% chromium. And again, just by using this basic diagram, I'm able to roughly figure out the composition of the system. And this is actually, again, a very powerful feature of these uh, phase diagrams, is that I can figure out A, how separation can occur, but B, the identity of critical complex alloys. However, one of the final things I want to emphasize is that all of these ternary mixtures have assumed a constant temperature. So you're often going to find a temperature value presented along with these ternary mixtures, just like we tend to have an assumption of a certain pressure when I'm looking at my binary phase diagrams. However, this means that as I change the temperature of the system, these phase diagrams will also tend to change. For example, if I'm looking at the equilibrium of ethanol, water, and chloroform, as I go to higher and higher temperatures, logically we'd expect this phase region to become smaller and smaller until the system becomes fully miscible under high temps. Because again, at this point, it doesn't matter whether you're nonpolar, polar, or somewhere in between. So using this, we can essentially evaluate our system, but it is worth noting that this does leave a certain constraint when evaluating these ternary phase diagrams. So this brings us to the end of physical mixtures. Next time, we're going to start by talking about chemical reactions. Until then, take care.